Hello, everybody, and welcome to my midterm review. For my topic, I chose relative age dating principles, and my name is Noah Dabler. Um, on eCore, it probably says Christopher, but I go by Noah. Anyway, let's just get right into the age dating principles. Now, the most important principle I'd say is uniformitarianism. The reason for this is because it states that all geologic processes that we observe today, we assume that they modified this pretty much the same way over all geologic time. And James Hutton, who's a Scottish geologist, basically said that the present is the key to the past. And what he means by that is that we have to explain history by looking at what we see today. We have to use the geologic processes that we see today to try and predict the past. And that's where these relative age dating principles came from. So we have to apply this principle of uniformitarianism because the only way for us to understand what happened in the past is to observe what we see in the present. And so using that, we start to transition into some of the most common relative age dating principles. And one of the easiest ones to understand is superposition. And basically what that means is when layers of rock are undisturbed, such as they're not, disrupted by plate tectonics or a volcano or something like that, the oldest rocks will be at the bottom and the youngest will be at the top. This one is pretty basic to understand. In essence, it means that it's a bit of a vertical timeline because it's impossible for a younger layer to slip before one previously deposited. If there's already a layer there, then how can a layer get under that entire layer? It's just not really possible. And while animals and plants may move between the layers and somewhat disturb these sediments in their deposits, which is known as bioturbation, it's never enough to change the actual positions of the layers. So, here's just kind of an example. Um, we see, looking at the key up here, you can see my cursor. We have limestone, shale, sandstone, and composite rocks. And over here we have a timeline as well, which kind of shows some of the eras. The eras, excuse me. We see the Precambrian era, which is divided into Proterozoic and Archean, and then Paleozoic rocks as well. And we notice, looking at the dates, these rocks are 541 million to 2.5 billion years old, and these ones down here are more than 2.5 billion years old. These ones are between 252 and 541 million years old. And as we can see, looking at these dates, the rocks at the bottom are older than the rocks at the top. So this layer of composite rocks down here where the Colorado River intersects, this is the oldest layer, and this layer of limestone at the very top, this is the top layer. And as we go from the bottom to the top, each layer is younger. So that is probably the most basic relative age dating principle. Next, we have original horizontality, which basically says that the deposition of these sediments occurs in horizontal beds, which means that the rocks themselves will form in horizontal layers. And the best way I could think to describe this is by looking at one of the biggest geological monuments in the United States and probably the world, which is the Grand Canyon as we see here. Now, the Grand Canyon has existed for a very long time, and despite all the erosion it's gone through for, probably millennia now, you can still kind of see that it is arranged in a horizontal way to where even though you go higher and it's very tall, obviously, you can still see that it's pretty horizontal. Just looking at my cursor now, you can see the horizontal layers as we go up, and it's very smooth. Even though a lot has happened to it over the years, you can still clearly see that as you go up, it's arranged in these horizontal layers. And that's what original horizontality is. All these sediments have collected together over a long period of time, and despite all the processes that have happened, these rocks are still in these horizontal layers right here. Next, we have cross-cutting relationships. Basically, what this means is that faults and igneous dikes are younger than the rocks they cut. However, this only applies to the layers that the fault or dike cuts through. And I have a little small example here. So basically, you can't cut through something that's not there. And I think one of the modules we went through compared it to a sidewalk with a crack. You can't make a crack in a sidewalk if the sidewalk isn't there. And an igneous dike or a fault is the same way. These layers have to be older than this dike because the dike can't cut through it if these layers aren't here. So judging by this picture, this bottom layer would be the oldest, then this layer, then the top layer, and then the dike would be the youngest thing in this picture because the layers that are there have to already be there to be cut through. So that's pretty simple to understand. That said, if say this dike was, just down here and it cut off around here, then this layer would still be younger than the dike because that dike does not cut through that layer. So, and since I found it kind of interesting to keep looking at these diagrams that show dikes, I wanted to actually look up what a real one looks like. And this right here that I'm going over right now, that is an igneous dike in this sedimentary rock layer. And you can also see this is another example of original horizontality because you can see that this giant ledge or whatever it is in horizontal layers. Moving on, we have one that is called inclusions, and this one is a little interesting because it's an example where a layer that is at the bottom might not actually be the oldest. And what inclusions are is it means that rocks that contain inclusions of pre-existing rocks must be older than the pre-existing rock. And I have this example here with these limestone, shale, sandstone, and granite layers. And if we look specifically at the granite and sandstone layers, we can see that little particles of this sandstone right here are embedded in the granite. I'm just scrolling over them right now. So this means that the sandstone is actually older than the granite, despite the fact that the sandstone is actually on top. And going by superposition, we would initially assume the granite would be older, but because there are inclusions of the sandstone in the granite right here, this means the sandstone must be older, because you can't embed the sandstone into granite without the sandstone being there first. So that's an example of an inclusion. And here we just have kind of a diagram, just real quick, that kind of has elements of all four principles we've described so far. We can see some inclusions here, this green layer going into this yellow layer. We can see that it has superposition right here, and we have a cross-cutting relationship, looks like a dike here, and original horizontality, which this layer here, the younger layer, this red layer right here, it has been, looks like cut, and there's kind of a river or some water formation that has been there, but we can still see that despite that cut, it still has its original horizontality on both sides. And judging by this, we use superposition to see this layer at the bottom is the oldest. Then the green layer is the second oldest. This yellow layer would be the third oldest because the inclusion shows that this green layer had to have formed before this yellow layer, and superposition also shows the yellow layer is younger. This red layer would be the second youngest layer, and then this purple igneous dike would be the youngest layer. Moving on, we have another important thing, which is fossil succession, and fossils occur in a geologic record in a definite chronological order. And how this can be used in relative age dating is that if you find, say, a trilobite, which is from a very old era, from the Ordovician era, then we know that it is very old. And if we find that in a layer, and then we find, say, a trilobite in the next era, which is in a later era, then we would know that the layer with the trilobite would have to be older than the layer with this trilobite. And this is just a graph which is for marine fossils. This applies to any fossil, but I just use this example to kind of remind us that while we talk a lot about sedimentary rocks, it seems we kind of talk about it like on a terranean level, as in, we're discussing stuff like the Grand Canyon and mountains and stuff. But we have to remember a large portion of these sedimentary rocks actually form underwater. So it's important to remember that and discuss marine fossils as well. And this is what I've kind of have here. So basically, the more left on this chart that the fossils are, the younger they are, the older they are. Excuse me. So if we find a layer of rock with these on the left, and then we find one with these blue ones here, then these ones to the left will be older than these. And finally, we have lateral continuity, and this one kind of says that layers of sediment initially extend laterally in all directions, and that even if they're separated by a valley or erosion, they're still laterally continuous. And this picture kind of displays that. It basically shows that here we see this little valley has formed. We've got this nice grass here. We have some trees here, and this is a nice little valley. And if we look on both sides, we see these two little ridges, I guess we'll call them. But you can see that if you look from side to side, you can see that this layer matches this layer. this layer is similar to this layer is similar to this layer, and this little layer at the bottom is also similar to this layer. So we can predict that even though this valley has formed, these are still very similar layers. They were once connected, and so we can predict that when this valley wasn't here, all these layers were connected together, and they were laterally continuous, and they were just nice smooth layers. And even though they've been separated by this valley, you can still see that they were once connected, that they're very similar, and that they were once probably laterally continuous and in a nice smooth layer. And that's basically it. I've got my works cited here. There's quite a few things about relative age dating principles. Obviously, it's not an absolute science like it says. It's relative. If you want more specific set dates, you usually have to go to absolute age dating, which includes stuff like radioactive half-lives and stuff like that, and you're analyzing isotopes and stuff like that to find their half-life to predict their age. But these relative age dating principles are good for basic dating. Like when you're comparing whole layers of rock, like I mentioned, you can use stuff like superposition, which we went over, um, original horizontality, the cross-cutting relationships with dikes, and here's another look at that dike. The inclusions. So if a layer is on top, but it has say sediments of itself in the bottom layer, like the sandstone and granite, and the sandstone is older. The Here's just a review once again, and then the fossil succession. If we find older fossils in a layer, then that layer must be older than a layer with younger fossils. And then the lateral continuity again, which is that even though these are separated by a valley, we can say that they were once laterally continuous because the layers extend laterally in all directions. So that's basically it. I hope you guys enjoyed watching. And yeah, I look forward to watching all of your videos. And I hope this kind of cleared up some of the relative age dating principles if you guys had any confusion. So thank you guys for watching, and have a great day, and good luck on your midterms.